So hello everyone, I'm very pleased to be here. My aim in the next 1 hour is to talk about the research of my colleagues and myself who work in my research group here at the School of Design and Environment at NUS. And this presentation will be a mixture of different topics at different levels at the intersection of geospatial data science, urban planning, computer science, and related topics. But nevertheless, I hope that you will all find something interesting for yourself. So I've been introduced. I don't have to say a few more words about myself, but I just want to say that I'm also assistant professor at the NUS Business School. I'm jointly appointed at two departments, architecture and real estate, which at NUS are at different schools. And I'm also involved in a couple of international organizations, such as the Open Geospatial Consortium. My research group has been established 2 years ago. We work on different kinds of research pertaining to urban data science, but mainly our three key areas of interest is spatial data infrastructure that is focused on buildings, digital twins at the urban scale, and data-driven urban studies. And in the next 1 hour, I'll be giving examples of a couple of projects that have been conducted recently by our researchers and students. For example, we just finished one study on urban morphology. This is a recent work by one of our master students in urban planning, Chen Wangyang. So together we've been developing the first application of deep learning in urban morphology. And I think this project is also quite interesting to mention because we always seek to study the latest developments in related fields such as computer vision, and then try to investigate how can we transport them to fields like urban planning and urban design. In this particular case, a workflow has been developed to automatically classify the urban form at a fine spatial scale across multiple cities. The workflow has been enabled using deep learning, and the result of this automated workflow using the latest computer vision techniques are maps of cities that indicate the urban form at a fine spatial resolution. We didn't really stop only at producing maps and data, but also we have been looking into applications of the generated data. So we've been investigating how can we relate the urban form that we have just automatically derived with various urban indicators such as vibrancy. And we have managed to establish the link between the urban form and vibrancy, and the results of this research help us to understand how can we design vibrant cities in future. This work will be published next week. We are quite proud of our master student Wang Yang, who has been mostly working on this topic. Another topic as another example of data-driven urban study that we have been occupied with recently is using computer vision on street view imagery to extract information. So one of our master students, in this case Koichi, also from the MUP program here at NUS, has developed a workflow to automatically assess the cycling appeal of streets solely from street view imagery. So he has realized that street view imagery contains a lot of hidden information about cycling that needs to be extracted. And he has developed a pipeline that automatically takes street view imagery at thousands of locations across the city to automatically assess bikeability at each of these points and produce maps that indicate how cyclable streets are at a fine resolution. This work has been implemented so far in Singapore and in Tokyo. Tokyo has been selected as another study area because Koichi is from there. Most of our research focuses on buildings. And we focus on buildings because, well, first of all, we cannot focus on everything, but buildings are one of the most prominent urban feature. So we mostly live in buildings, we work in buildings usually. Buildings are one of the largest consumers of energy, and buildings are one of the most prominent features of the urban environment. That's why most of our research is actually focused on buildings. And this is what I'm going to talk about. How can we, how do we extract data on buildings, and how do we use this data to derive informed decisions in the context of urban planning? We are not, of course, the first one to work on this topic. Data on building has been important for many years across different disciplines. So data on buildings is important, for example, to assess the living conditions for socially sustainable areas. Data on buildings is important to monitor the evolution of the urban form and study urban transformation. Data on buildings, in short, has many different applications, and that's why it's really important in fields like urban planning. Another particularity about data on buildings, why we find it so interesting that we decided to spend most of our time on it, is that data on buildings comes in different shapes and flavors. Data on buildings can come in the form of 2D footprints. It can come in the form of even spreadsheets or 3D models. And data on buildings can also be associated with time series, which is another interesting extension. When talking about research agenda of a research group, it's always important to give some context. This research direction and research agenda didn't just come up out of nowhere. Our research agenda has been shaped by some context and developments in the recent years in the geospatial and urban data world. These are quite exciting times for urban data scientists and applying AI in cities. One of the most common and important trends is open data. And open data is not only relevant these days because there are more and more datasets released openly, and more different kinds of datasets released, but also because we have multiple actors engaged in this process. First of all, we have governments releasing open data. We have companies. We have academia, for example. We also tend to release some data openly. And fourth, no less important, is that the crowdsourcing community, that is volunteer geoinformation, has been quite active in the past few years. Some other trends that we have noticed is that we see new types of data being released openly, potentially leading to new insights in the built environment. We see a trend I like to call amplification that I will explain a bit later. Open data has been increasingly recognized as being important across multiple disciplines. And also, another important trend is the collaboration between these actors. Until a few years ago, they have all been stuck into silos. Governments have been working alone. Industry has also been working, on the other hand, in their own silo, but now we are seeing increasingly a collaboration among them. So let me clarify this with some examples. First of all, governments lead the way when it comes to open urban data. So nowadays, many governments around the world, especially in developed countries, have their open data portals where everyone can download hundreds of different types of data for any purpose for free. Singapore has established its data portal a long time ago. Another trend we are seeing is the deregulation of data. One of the biggest news this year in the geospatial sector was coming from India, which has enacted a new law that all data, all geospatial data that is produced by the government or with taxpayers' money has to be released openly. And news like this is becoming more frequent around the world. India is not alone, but I find India the most fascinating example because it's a huge country, so you can imagine the quite positive impact this legislation will have in the next few years when all these data sets become open. Companies are also becoming more and more active. For example, Microsoft has been working on mapping buildings around the world. They have released open data on all the buildings in the United States. So anyone can download this data set that contains footprints of 129 million buildings around the world, in the United States. Just a few weeks ago, I've been quite happy to see this announcement by Google. Google has mapped all buildings in Africa and released this data set openly as well. So this is how the industry also contributes to the landscape of open urban data, especially data that is focused on buildings, which makes us quite happy because this is our main research interest. As academics, we also have some interesting developments. We are involved in not only creating open data, but also creating open software to deal with such data, and as well as developing open standards. We have even our own journal where we publish research on this topic. And the fourth actor is a crowdsourcing community, most importantly, OpenStreetMap. One really important development is that OpenStreetMap has been growing in volume of data, but also in quality. So, for example, this is a screenshot from OpenStreetMap from Bangkok in Thailand. And as you can see, the city is mapped pretty well. For those who are not familiar with OpenStreetMap, I suggest you to try to acquaint yourself because it's becoming more and more important also in research and teaching. And for those of you who are going to take my GIS course this semester, you might be interested to hear that OpenStreetMap will be one of the main topics we are going to talk about. And really, OpenStreetMap, the developments have been quite fascinating. So earlier this year, we have seen the 100 million edit in OpenStreetMap. And now more than 500 million buildings around the world are mapped in OpenStreetMap. And because of the crowdsourcing and completely open nature of OpenStreetMap, anyone can use this data for any purpose, even commercial purposes. Another trend in the urban data landscape is that we are seeing new types of open data. Most prominently, we are seeing the rise of crowdsourced street view imagery. I think almost all of you here know Google Street View. Those of you who are coming from China are probably acquainted with Baidu Maps and Tencent. Street view imagery is not new. it's been with us for about 10 years. But what's new is the rise of the crowdsourced counterparts, services like Mapillary and CartaView, where in which everyone can upload their own street view imagery. And this is an example of one street view image obtained from Mapillary in the Marina Bay area. So anyone can upload their street level imagery, and anyone can download this data for any kind of purpose. And at the moment, we are looking how to leverage on this data for new kinds of applications. Predominantly, we are looking to investigate how can we extract information on buildings, like material, but also, as I have shown a few slides earlier, we are looking into applications like bikeability. Another new kind of data that is not exactly new, but is rapidly gaining momentum are 3D city models and urban digital twins at a broader scope. Collaboration between these actors plays an important role in the past years. So before all these actors, government, companies, academia, and OpenStreetMap, they've been quite disconnected. But in the past few years, we are seeing them coming together. And we are seeing boundaries among them fading. For example, one of the most important trends is that companies started contributing to OpenStreetMap. This is quite interesting because they're investing their own funds and manpower to map roads, to map buildings in OpenStreetMap. And as a result, anyone can use this data, even competing companies. And no less important is the trend of recognition. So cities and national governments started to recognize the economic benefit of open data. For example, the Danish government conducted a study a few years ago on the economic benefit, and they have realized that for every Danish crown invested in collecting data that is released openly, the GDP has a benefit of 3 Danish crowns. And amplification is also an important trend. So interestingly, open data, when it's released, it doesn't stop there, but it may result in further forms of open data, and it sparks new applications and use cases. For example, recently my former colleagues in the Netherlands, they have taken a few open data sets released by the government, and they put them together and they created an entirely new data set, a countrywide 3D model. So this is an entirely new data set that has been created thanks to existing open data. And this data set has also been released openly, contributing back to the landscape of urban data. So that's all about the context. In brief, data on buildings is becoming more and more prominent. It's available in more and more locations. We have governments that are more open and willing to release data. We have more use cases, we see more interest, but still there is a lot left to be done. For example, one of the key issues in data on buildings is that the coverage is still heterogeneous. So we still see a lot of cities and countries that are being entirely unmapped or that they're partially mapped. At the example above, you can see a screenshot of OpenStreetMap from, I think this is Batam. You can see all the streets mapped, but almost no buildings are mapped. So data on buildings still lags behind other kinds of geospatial data like streets. Another issue is that data on buildings is often not harmonized. It means that there are different kind of format, different kind of standards, and we have all these governments that release data in disconnected initiatives that don't have much overlap. Data on buildings is often not entirely understood by users. So people download the data, they never check the quality, and that may result in issues when the data is used for analysis. We also think that novel AI techniques are underapplied. There is still much to be done. And use cases of buildings, of data on buildings are plentiful, but still they are kind of in status quo. There are no really many new use cases being invented in the past few years. And finally, one opportunity in this research line is that data sources such as Street View imagery are completely underused. So we all know about Google Street View, but when it comes to using it to collect data on buildings, it's almost completely underused. So our research group tackles all these research opportunities and gaps, and our mission is to use novel techniques to explore new data sources and cut across multiple disciplines to make data on buildings more comprehensive, more accessible, more interoperable, more maintainable, and more usable. And for that, we have designed a holistic research agenda dealing with geospatial data on buildings from the very beginning, acquiring data, to the very end, understanding the quality and using it for a particular purpose. And I'd like to introduce you to our research line by explaining you 4 topics we are working on. First is understanding spatial data quality. Second is our contribution to increase the availability of data. Third is to process the data to augment and amplify its value. And fourth is to develop completely new use cases on how to use this data on buildings to increase its value even further. At the core of our research agenda lies quality. We think that you can use spatial data on buildings only if you can understand its quality entirely. And that's why in the past few years, we have been working on this topic. We have realized that even though quality of spatial data on buildings is important, there are quite some notable gaps. So there is little known about quality assessment. There is a lot of open data. The volume of open data is increasing, but it is often not evaluated. It is often not understood what is the quality of this open data I've been talking about. Little is known about benchmarking open data and setting standards for best practices. For example, there is really no like a yardstick, no gold standard for aspects like what is the level of content of the data and what is the update frequency. So as a consequence, governments are not really aware how well they stand when it comes to their open geodata efforts. Are they better than other governments? Are they comparable? And so on. And we think that we are in a great position to work on this topic because as a university, we are non-commercial, we are non-governmental, and we have the capacity to innovate new kinds of methods. In this topic, one of the key projects that we have just finished is on benchmarking authoritative data sets on buildings. So our latest project called Open Government Building Data benchmarks more than 100 cities and countries around the world that have released data on buildings openly. So what we have done is we have spent a few months on identifying all sources of data on buildings that are released by the governments around the world. And we have downloaded all this data and started digging into it. So we have been analyzing what kind of information is available for each building. Is the data released in open formats? Is the data valid? When it was updated last time and how frequently it was updated. And as a result, in our database, we have more than 100 million buildings that we have analyzed. This project is completely open. So on our website, you can visit the project page and you can check out the map, which is also screenshotted here, with all the locations around the world where you can find data on buildings released by the government. But probably more important for the geospatial crowd, we got our hands dirty with the data. So we try to understand what are the practices of governments, what kind of information they release on buildings beyond the geospatial content. So we realized that half of the data sets have no semantic content whatsoever. For example, some governments release data on the type of each building, on the height of each building, on the address, but half of the governments don't release any kind of such data. Another disparity we found is that the update frequency is not standardized. So many of these data sets have not been updated for more than a year. And that can be a huge issue because some spatial analysis rely on up-to-date data on buildings. What we found also interesting is that for some governments, this was a one-time adventure. So some data sets have been released only once, and the government didn't bother to update the data set again. Some of the data sets have been more than 10 years old. And another really interesting point is that OpenStreetMap in many places provides better data than the official government data. And that led us to another topic, and that is assessing the quality of OpenStreetMap. So OpenStreetMap is becoming more and more relevant. The dataset is now huge, and it's being used by many different stakeholders for many different kinds of spatial analysis. However, while the OpenStreetMap data is global, it remains highly heterogeneous. Some locations around the world are mapped very well, like Singapore, while some of them are not mapped at all. And yet, we don't really know the quality of any of these locations. Usually what we are interested in is to understand for each location whether all the buildings are mapped, or if they're not mapped, what is the percentage of buildings that are mapped. And those of you who are not really acquainted with geospatial topics may be surprised to learn that there is simply no technique to understand this. So for many locations around the world, we simply don't know what is the percentage and quality of data that is mapped in OpenStreetMap. And second, even if we have everything mapped, we are interested to know what is the accuracy of this data. Such assessments are mostly local. They are done by comparing OpenStreetMap to official government data or to satellite images. They can be conducted manually or automatically. For example, the content of OpenStreetMap is compared to government data, and then their difference indicates the quality of the dataset. For example, we can take the buildings in a government dataset, we can compare it to the buildings in OpenStreetMap, and we can understand what is the percentage of buildings that is mapped in OpenStreetMap. An alternative approach is to do the same using satellite imagery. And we've done that actually for Singapore already. We realized that Singapore is very well mapped. 98% of the buildings are mapped in OpenStreetMap. And accuracy is not that great, but it's also not terrible. On average, the positional error of buildings is 3 to 4 meters. So the next logical step is to understand what is the quality of this data around the world, not only specifically focusing on a particular location like Singapore. This topic is important because now we have more than 500 million buildings mapped in OpenStreetMap, and we really don't know the actual completeness. Because first of all, we don't really know how many buildings there are in the world. So the topic we've been working on is how can we scale such local analysis globally to understand what is the global completeness of OpenStreetMap data and understand whether everyone in a particular city can use, whether the OpenStreetMap dataset in a particular city is good enough to be used by anyone. And turns out that doing it is a bit more difficult than it sounds, because doing the same local analysis regionally or even globally is simply not feasible and possible. One of the reasons is that we simply don't have government data on all buildings around the world. So we cannot compare the content of OpenStreetMap to the authoritative dataset. Second, we also don't have satellite images at a high resolution for the entire world. And even if we had, this dataset would be so big that it would be simply impossible to process it. So what we have done in this arena is that we have developed a completely new approach to assess spatial data quality. This new approach is AI-driven and it is intrinsic. We have realized that to assess the quality of OpenStreetMap data, we might not necessarily need any other dataset to compare OpenStreetMap to. That's why this method is called intrinsic. We have realized that we can take OpenStreetMap and through an AI approach, we can automatically figure out the number of buildings that are missing in a particular city. So we have done that by computing a series of urban morphological metrics that provide a unique signature for each city. And this signature, or like a fingerprint that each city has, can hint at the number of buildings that the city has. And what we have done afterwards is compared how many buildings there are in OpenStreetMap and how many buildings we think there is in a particular city thanks to our AI-driven intrinsic approach. And the difference is the quality measure. Now we are experimenting with this method across Southeast Asia. And once we advance it, we will scale it globally. This research has also helped us to understand some really, really interesting cases around the world in OpenStreetMap. For example, this is Kediri, a town in Indonesia that has a really, really interesting case about OpenStreetMap quality. And it also suggests why this topic is quite important. So Kediri is a relatively small city, but its quality is highly heterogeneous. One of the districts in the city is mapped almost perfectly, while another district in the same city has almost no buildings mapped. So during our exploration, we have been thinking about what is the relationship between all these actors, between governments and OpenStreetMap. Because one of the natural questions that arises is, if a government releases a data set openly, why do we need to care about OpenStreetMap? Why don't we simply use the government data set? Is there any purpose of having OpenStreetMap in the same city and a parallel data set? So we spent some time contemplating on this topic, and we have looked into existing practices, and we realized that the bond between the government and OpenStreetMap is stronger than it appears. So we realized that in some cases, governments are taking data from OpenStreetMap to integrate it in their government datasets. So they rely on the community and local knowledge to extract additional information that they didn't plan to extract. And on the other hand, the OpenStreetMap community also relies on government for some information that they might not be able to extract. For example, year of construction of particular buildings. And we realized that these two sources, in conclusion, are not competing, but they actually go well together. And we believe that the future of data on buildings is integrating all these data sets together and take advantages of each of these actors. Okay, so the second research line is increasing the availability of data. As you have realized, data is plentiful, but it's not everywhere. So what can we do to increase the availability? One key issue of OpenStreetMap is that buildings are not mapped everywhere. But one advantage of OpenStreetMap is that roads are almost mapped everywhere. This is an example from Indonesia that I have shown earlier, where almost all roads in a city are mapped, but less than 5% of buildings are mapped. At the same time, as a human, just looking at these street networks, you can make a conclusion that, yeah, this looks like a built-up area, looks like a city, a densely populated city, and there should be buildings there, but they're not mapped. So what we've been working on in the past months, thanks to our AI specialist, Abraham, we've been developing a completely new approach to fill the content of maps. A completely new approach to generate spatial data, taking advantage of the marriage between street networks and buildings. As part of this research, we have developed GenMapper, which we have released as open source. GenMapper is a tool that relies on generative adversarial networks, which is a relatively new approach in computer vision that is able to take only the data of roads as input, and it figures out where the buildings are supposed to be, what is their number, and what are their shapes. GenMapper has been trained on 9 cities with different urban morphologies around the world. And preliminary results suggest that the method is reliable enough to be used to create new maps of buildings where such data is not available. These are some examples of the 9 cities. As you can see on a quick look, in most of the cases, the method works. It's able to roughly predict the urban form, roughly how the buildings look like, where are they, and their amount. Obviously, the method is not able to predict one-to-one building footprints, but we still believe that there are many applications of this approach because it can be used to reveal the approximate urban form in locations where such data didn't exist before. And second, it can help us to estimate the total number of buildings and how they look like, and urban morphology metrics such as the built-up area in a neighborhood. This software that we have just developed a few weeks ago has been released as open source software on our GitHub repository. And we also just finished a paper, and the paper is available as well. Okay, so how does this all fit in places like Singapore, where we have data, where we don't need to map many new things? We've been active here as well. So we've been looking how to leverage on existing data in OpenStreetMap to increase their dimension and create 3D city models. We started with Singapore, and we created an open 3D model that we have released as open data, and anyone can download it and use it for any purpose. We continued the work in other capitals of Southeast Asia, and soon we hope to have open 3D datasets of all these cities. But at the moment, we are working on identifying what is the quality of existing OpenStreetMap data in all of these cities to understand whether it makes sense to generate these 3D models. All right, the third research direction we've been working on is not understanding data, not creating data, but to process existing data to add value. And most importantly, one of the current research activities is urban morphology. So we've been working on taking advantage of this huge amount of open data on buildings from OpenStreetMap and governments to process them and to compute metrics that characterize the urban form. For those of you who are not familiar with urban morphology, in brief, there is a theory that the shapes of cities are shaping activities, and these shapes of cities are quantified using a series of urban morphology metrics. These metrics are plentiful, they're quite diverse. For example, some of them indicate what is the distance between buildings in a city. Some of them indicate what is the complexity of building footprints, and so on. There are hundreds of these metrics, and they have been found critical for a variety of disciplines, not only urban planning, but for example, climate studies and energy simulations. And studies have been mostly focusing on understanding the association of these metrics with aspects such as livability and efficiency of cities. But one shortcoming that we have identified in this research is that buildings are not really in focus. Most researchers focus mostly on road networks. So most of the urban morphology field has been analyzing street networks rather than buildings. Another gap is that even though many people have been working on this topic, there are no really tools or open software that can help us to compute all these metrics easily and efficiently. Most of the tools that people have been using are commercial tools, or they have been developing their own tools, but they have never shared it with the community. And another shortcoming is that there is no large-scale data on urban morphology. So researchers mostly compute these metrics for their study, and they never release this dataset openly. So if you want to conduct your own urban morphology study, for example, in Singapore, you have to figure out the whole process on your own. You cannot simply download a data set on these metrics from somewhere and use it out of the box for your analysis. And that's where our activities come in. We started a project called Global Building Morphology Indicators. The goal of this project is to compute urban form metrics for all the urban areas around the world. So far, we have a prototype developed on 20 cities around the world with more than 100 indicators. We are computing these metrics at multiple scales, at the national level, city level, regional level, neighborhood level, and micro level. And we are also computing these metrics at the building level. So for those who are current students in this master program, you might find it beneficial to learn that we are going to release the first version of this data set next month. And anyone, of course, can use it for any purpose. There are no restrictions or licenses. And in this project, I have to acknowledge the support by our friends from Amazon. So we've been running this project on a supercomputing, on a high performance computing infrastructure. When this project finishes, it's going to be the largest repository of urban morphology metrics in the world. And the reason why we had to work together with Amazon is that this is a computationally very intensive project. It's truly a big data project. We have hundreds of billions of records. Just to get an impression of one of the results, on the right side, I included a screenshot of the dataset from Singapore that is ready and is going to be released openly soon. One of the metrics is the average distance among buildings at the 100-meter level. So in this particular case, I think you can all discern different urban areas in Singapore. You can see, by the way, the areas that are darker in color are those where the distance is smaller, and those that are lighter is where the distance is larger. So you can recognize darker areas like East Coast, where we have more landed houses, meaning that the distance between buildings is quite small. On the other hand, we can recognize lighter areas where public housing or high-rises dominate, where the distance between the buildings is much larger than between landed houses, for example. And data like this can be found of use in, let's say, microclimate studies. You can use data on the distance among buildings to understand the wind flow and the impact of the urban form on the microclimate. And yeah, Amazon has been a really good partner in this project. They have even been marketing this data set. Okay, and the final topic I'd like to spend my last 5 to 6 minutes on this is developing new use cases on data on buildings. So all these topics, yeah, they might be cool, but data on buildings is useless if we don't really use it. There have been many different use cases on buildings in the past years, but our impression was that there is a status quo on this topic. Data on buildings didn't really see any new innovation in the past years when it comes to use cases and applications. And to try to contribute to this topic, we have been looking into rooftops, which nowadays is a hot topic, especially in Singapore. So rooftops have quite a potential for, say, solar panels, green roofs, even growing food. And the mainstream research that uses data on buildings has been mostly focusing on quantifying the potential of buildings for all these purposes. For example, there was this study from Switzerland last year. A team from EPFL has taken building data of all buildings in Switzerland and has analyzed what happens if we put solar panels on at least half of the buildings in Switzerland. And research like this has been done pretty much everywhere. So quantifying potential has been done also in Singapore, in other countries in Southeast Asia. So it's nothing special anymore. And another mainstream research line is identifying the best locations. Like say you work for the government, you have money to buy solar panels to put across the city. Building data has been used also to identify what are the best locations, for example, to put solar panels. Yeah, all that is cool. We know what happens in future, we know the potential, but one notable research gap that we have noticed is that we don't know what is the current situation and actual status today. So how many buildings at the moment have solar panels on the rooftop? How many have farms? How many have green roofs? Surprisingly, this has not been developed. Also, another research gap that we have noticed is that there is no centralized registry of rooftop data. Like, no one knows how many rooftops there are, how are they used in a city, at least not openly. Also, there is no research that includes multiple types of rooftops. Some of the research uses binary information, like whether a rooftop is occupied or not. But there is really no research that understands the content of the rooftop, whether there is a solar panel on top of it, or a water tank, or a green roof, or nothing. So the key research gap we realize is that there is no detection of the content of rooftops, and also there is no way to explain the content. So even if you know how many solar panels there are on rooftops in a city, we don't really have mechanisms to explain why are there so many solar panels, or why are there so many green roofs, or why so many rooftops are simply empty. And this is a research gap that we have been tackling last year. We have been using satellite imagery and computer vision techniques to automatically map the content of rooftops in many cities around the world. Our project, which we dubbed Roofpedia, is the first such project in the world. We have mapped the content of 17 cities, in total 1 million buildings, to understand the prevalence of two things, of green roofs and solar panels. And on this slide, you can see an example for Singapore. These are all the rooftop solar panels that we have detected automatically in the city. Our project also presents the first global open registry of roofs for urban sustainability. Roofpedia is composed of 3 pillars. The first one is the computer vision part, that is the detection of solar panels and vegetation on rooftops. For that, we use deep learning. And after we detect a particular feature on each rooftop, we tag the content in OpenStreetMap. The second pillar is the registry. So we thought it would be really useful for other researchers as well to have this data on the spatial distribution of green roofs and solar panels in a city. And so far we have this open registry for 17 cities around the world. And third is aggregating this data at the city scale to understand the prevalence of solar panels, and green roofs in a city. So far, among these 17 cities, we have realized that Las Vegas is the most successful when it comes to utilizing rooftop space for solar panels, while when it comes to greenery, Zurich in Switzerland is the city with most green roofs in the world. Okay, these are more examples. This is in particular Manhattan. All the buildings with either solar panels or green roofs are colored. So why is this data important? We think there are new use cases that can spin off out of our project. First, we can use data from Roofpedia to track the current capacity of renewable energy production and carbon offsetting in cities. Now we have an easier mechanism and instrument to understand how many solar panels there are in a city. And therefore, subsequently, we can understand what is the capacity of renewable energy production. Also, for those who are more into urban planning, you may find this project useful for rooftop compliance. This data can also be used to monitor the effectiveness of government urban policies and subsidies. For example, we have realized that yes, Zurich in Switzerland is the best city in the world when it comes to green roofs, but we didn't really understand why that happens. So digging a bit further, we have discovered that Zurich has strong government policies mandating green roofs on all new buildings. And that means that data derived from our project can be used exactly for that purpose, to monitor how effective urban policies and subsidies are. The same goes for solar panels. For example, a local government can give subsidies to install solar roofs, and in a few years, Roofpedia can be used to track how this policy has been successful. Another use case I see in future is verifying pledges made by businesses. So today, many companies are pledging to become carbon neutral. They're pledging that they will install a certain amount of solar panels, but there is no real instrument to verify all these pledges. And we hope that Roofpedia can be used for that purpose. Okay, I'll skip this because of lack of time. So I'd like to conclude this talk by highlighting 3 trends I see from our perspective that pertain to geospatial data science and the use of AI technologies in cities. First, I think that crowdsourced data, especially crowdsourced street view imagery, will only grow in importance, especially in geographies like Southeast Asia, where governments are not always open in releasing data openly. And because these locations, especially across Southeast Asia, are seeing a certain data set for the first time, we might see novel use cases coming out from these countries. Second, with a growing volume of geospatial data, we think it's essential to set up some mechanisms to benchmark them and assess their quality automatically. Quality of data is not a new topic for sure, but there is still so much to be done, especially in the automation part. We think that urban data scientists who don't have a geospatial background tend to take data for granted, and we hope to be able to contribute by raising the awareness about the quality of data. And third, new techniques like GAN remain underused and offer a lot of potential in geoscience. We can use these techniques, transporting them from computer science to the geospatial world, to improve the quality of data, completeness, and reliability. So I hope that you found some bits of this presentation interesting for what you're working on in your background. If you'd like to learn more about some particular aspects of the work, you're welcome to connect with us, to check our website. We are also active on social media. We have a Twitter account, we have a LinkedIn page, so feel free to explore our work.